Hello guys, good evening. My name is Mohammad Sabir and today I am here with you. In these sessions, we are going to start with the topic that is related to manufacturing science. We are going to learn mechanics of metal cutting. What basically you understand by the mechanics of metal cutting? You know how to uh, we like how to cut the metals, like how to cut the metallic workpiece by using a tool. Okay, the shearing action is occurs. First, we will try to visualize the how the workpiece is being machined by a tool. Okay, basically, let's assume this is a basically a simple workpiece, and this basically is a tool. Okay, like the first need to cut the workpiece is what is basically the strength of the strength of the tool is much more than is it should the strength of the tool should be more than strength of workpiece. Okay, this is the first requirement, the first need to cut a workpiece by using a tool. uh, like this when our objective is to machine at this surface. Okay, then when first we apply a load, like apply a touch the tool. Okay, and then apply a cutting force. As we increase the magnitude of cutting force, what will happen to the workpiece is basically shearing action is occur. What basically shearing actions, in a machine design, like in a strength of material, you learn about the stress strain curve. This is a stress strain curve. What will happen basically, yielding occurs load at which the stress is becomes equal to the yielding stress. In that time, you can say like the failures occur. The chip is removed from a workpiece. The chip is removed from a workpiece. Like we can apply this stress strain curve, like on every point. You should keep in your mind. This is a basically the curve for, we define this stress strain curve for a point stress, like at a point. Okay, like is basically we can apply anywhere. Okay, and now we will move to the, okay, like this we we basically saw that how the workpiece is being machined by a tool. Okay, this is a machine by a tool, and as the shearing action is occur, the yielding like shearing action is occur. If we assume that the workpiece is a ductile, the shearing action is occur. When we assume that the workpiece is brittle, and then the crack propagations phenomena occurs. Okay, is happening. And now we will go the other sections, the orthogonal cutting, and that's are not the case of a science. It's a basic a term. We will go for the what is the science behind of a metal cutting. And now we will first, like how to model this metal cutting phenomena. Okay, like how to analyze that, like our interest to find out, okay, how much friction, how much friction is generated, and how much shearing force is occurring. And these type of questions we want to answer it. Like for that we are going to uh, generate some mathematical model, and like some kind of equation we should have. Therefore we can analyze mathematically and tune that, okay, uh, what is input parameter for the particular output parameters, like what is the cutting power. That's a lot of steps we are going to deal in that uh, problem in that session. Okay, then we go there, we go for the basically this it's basically it's basically this is basically yeah, yes, this is a picture. Basically, this is a picture of orthogonal cutting model. It's a 2D model. Basically, it's a simple kind of orthogonal cutting model, and then this model is basically is the model can be modified and can be extended for the turning. Okay, like first we try to analyze this model. After that, we will go for the turning. This is a kind of like a practically we we want to analyze a turning. The first we analyze that this, and further we will go for that. This basically the workpiece and workpiece tool interactions. Here you can say this is a rack angle, this is a shear angle. This is a basic kind of geometrical parameters. It's not a scientific parameter. Like it's there will be no science behind it. It's a basic geometrical parameters. Okay, and we try to like we have a depth of cut. You also can you also can you also can say this is a depth of cut is equal to uncut chip thickness, and this is a basic chip thickness. Chip thickness what after cutting what will be the width of the chip is the chip thickness. Depth of a cut is what means it's a basically uncut chip thickness or chip thickness after before cutting. Okay, this is a shear angle. Shear angle is what? Shear angle is what like where uh, the shearing occurs, the angle between horizontal to shear plane. This basically is called as a shear angle. Okay, this basically is called as is a represented by a phi. This is represented by a phi. This is alpha, and easily you can by using a simple mathematics and similarity principles, you can uh, develop this relation that is basically a chip thickness ratio is what T naught upon T c is equal to sine phi cos phi minus alpha. These are very basic uh, relations, expressions you easily can find out by using the mathematics. Okay, there will be no physics behind it. Okay, now we will go for the now we will go for the force analysis of a metal cutting. This is a very interesting part because this this analysis is used to is used to model the temperature profiles, and also we can predict the energy distributions over a workpiece and tool. Okay, there are a lot of questions we can answer by using this merchant circle diagram analysis. Okay, it's a very simple kind of analysis, merchant circle diagram analysis. There are a lot of assumptions are there. Okay, and then Lee Schaffer. There are a lot of extended version is also be there, but as a fundamental as a fundamentally we want to analyze the first merchant circle diagram, then we will go for the Lesha for there are a lot of Ernest model. Okay, this is a merchant circle diagram. What basically happen in a merchant circle diagram, it's a simple kind of mechanics. Okay, so it's a simple kind of mechanics. We will try to visualize it, see what will happen. Basically the first we have to focus on to understand the what physics behind it. Okay, like what actually is happening, like how to approach the problem, how to model this problem, and how to apply the mechanics into this problem. The first thing is that when we touch the tool to the workpiece, what will happen? Basically, we apply a cutting force. We apply a cutting force. Easily, you can see that the cutting force is applied to the tool by moment nature external power. So that is PZ is a cutting force. the component of a cutting force Pz and Pxy. The both of the component of cutting force are basically the most contributing factor is Pz. The most contributing factor is what? Pz. The net of Pz R is what? The net resultant of the Pz and Pxy is what? R. This basically is the please attentions on what I'm saying. Please take attention on what I'm saying because these words are so important. Okay, first you understand that this are basically two workpiece interactions. The PZ is what? Is a cutting force. Is basically it is applied. It is applied by a actional power source, the tool, and that is transferred by there's a transfer to the workpiece by using a reactions force and internal shearing actions. That is transferred to the workpiece by using a shearing action. That is kind you can understand. This is a PS. PS is what? Is the shear force, and PN is what? PN is what? The normal shear force, and the resultant is what? R. Same. The magnitude is same as well. Is same uh, as the previous resultant. Okay, and you can understand, and simply like when we apply a force to that tool, uh, some friction is always be there. Due to that, this tool basically feels a friction between tool and workpiece, and because of that the chip also feel the frictions and normal force. For that this is basically a this basically a this is basically a friction. This is basically friction. This is a normal force. Basically, this is a FBD of is what? This is a FBD of a chip, and this is a FBD of a tool. Like PZ and PXY is applied on a tool, and friction and steering action is applied on a chip. Okay, that should be keep in your mind before there is a big blunder. Okay, according to you can design this problem. At an equilibrium, there? What should be there? The the friction, the force which is generated by a friction normal is equal to the force which is generated by the shear normal shear and shearing force. Okay, because this is a continuous is a constant velocity. This is a constant velocity chip formations. Like the chip is formed with a constant uniform velocity. Okay, the velocity change is not there. So what? The equilibrium should be maintained. Equilibrium should be maintained. Okay, that should be maintained. Please keep in your mind. Please keep attention on the word. Okay, please keep attention on the word. And this is basically is what this is a simple kind of back angle neta. This is a beta. Easily you can find out. Easily you can. This is a simple mechanics problem, like how to uh, take a component and equate it, and then easily you can find out these stuffs, these expressions. And now we want to tell us something about a merchant circle diagram. Basically, a merchant circle diagram is used to find out the neta and a friction force, normal force, shear force. Because experimentally, PZ and PXY is can be find out uh, experimentally. But this is the F, N, and PS and P, and this is the theoretical parameters. Okay. So what we will go for the merchant circle diagram analysis that gives the value of neta, and easily we can choose a cutting fluid according to that. Because if we have an idea about neta, we like what is the friction factor, or what is the coefficient of friction is, what will be the coefficient friction between workpiece and tool, then accordingly uh, we can choose our cutting fluid. Okay, that is a basic kind of analysis. And then we will go for these are limitations and advantage. You can refer it like in other next lectures. We basically we will discuss these stuffs. And for today's we basically want to give some science, some physics features of the Merchant circle diagram, and want to give us some flavor of physics and what science behind it. Okay, what physics laws is applied here. That's like we are looking for that. Like we want to look into that. Okay, and then we will go for the now. Now the like we have a basically in the section we have a three force. The basically is what we have a three force. Basically is a shear force, and Pz is cutting force, F is a friction force. Okay, is Pz is what? Pz basically it's a cutting force, Ps is shear force, which is which is responsible for the shearing actions, and F is what is basically is responsible for the heat generation. Okay, due to a friction, heat is generated. Okay, so you also can say the whatever power we deliver to the chip, whatever power we deliver to the chip, basically is converted is basically is distributed over a two section. One is one is for shearing, another is for heat generation. That is very important thing, because by using this kind of approach you can predict the shear zone temperature of a workpiece. Okay, like in next sessions we will look into that. Like what is a shear velocity, what is the chip velocity, then we these type of stuffs we will cover in the next sessions. In today's it's like keep learning, and whatever doubt you have you can ask in your on comment section. Thank you, all the best.